your desktop or a workstation into a supercomputer. You can get the computing facility by using the concept of GPU computing. Okay, so I'm going to talk about that. Okay, just wait a minute. Let me share my screen. Abba, full screen is visible. Yes, you guys.
नो सर, अभी फुल स्क्रीन नहीं है।
Full screen नहीं है. Okay, just wait a minute. What about now?
यस सर।
Okay, good. So I'm going to talk about parallel computing using GPU, how we can use our graphics processing unit to perform the parallel computing. Okay, so this is the content which I'm going to present this session, talk about in this session, introduction, some of the basics, how we reach to this GPU computing concept, are what are the things which are uh, internally processed by the GPU computing, or in GPU computing using what are the concepts. So then what is the graphics processing unit? After that, we will talk about what is this GPU. GPU is actually the GPU computing, general purpose computing. Like GPUs were created for the graphics operation, but now we are using the GPUs for scientific and general purpose applications. So that's the concept of GPU, and sometimes called GPU computing as well. And then when and why to use the GPU. It's not always feasible to use the parallel computing concept. There are some features should be available in your problem. Then only we are going to use the GPU concept. Then we will talk about the CUDA. CUDA is Compute Unified Device Architecture, which is made available by the NVIDIA, and it's good for NVIDIA's GPU. Okay, it's not a generalized one. It's just for the NVIDIA's GPU, but it's really good. That's why we are talking about it. Okay, then we talk about the CUDA hardware model, how the CUDA understand the internal structure of a GPU. Then the CUDA programming model to map our problem to that hardware or GPU. How what should be the architecture we will follow in the programming side? We will talk about that. Our logical composition, what we are required. Then some of the examples where we have achieved the speed up during the GPU using the GPU computing concept. Then some of the latest supercomputers which are built with the help of GPUs, and a demo video which is supporting why we should go for the GPU computing concepts. Okay. Okay, so let's start. GPU computing is actually a type of heterogeneous computing. So, what is the heterogeneous computing? Heterogeneous computing means where we are going to use the different types of processing unit to speed up our solution or improve the performance. Okay, like in case of GPU computing, what we are doing, we are using CPU with the GPU. Okay, sometime what we do, we use the filled programmable gate array FPGA with the CPU. So these are also a kind of heterogeneous computing. Okay, where we design a application specific hardware and burn it into the FPGA, and that FPGA is associated with the CPU to speed up the problem or find the fast solution of our problem. Okay, so what is happening in case of heterogeneous computing? There should be a CPU, there should be a CPU, and with CPU we are going to attach a accelerator core. Accelerator core is our GPU. In our example, in case of GPU computing, accelerator code is going to be a GPU. Okay, so this GPU is not going to work its own. It's always required to be a CPU. It's always required a CPU. CPU is actually going to manage everything. It's going to manage the complete control flow of our program. Only the compute intensive part where we required some repetitive operation, that will be offloaded to the GPU side. Okay, but all the control flow operation and resource management all will be done by our CPU. So the GPU is not going to work independently. They are always going to work with the CPU. GPU is not going to be work independently. Okay, I was talking about. Okay, so how we reach that the concept of GPU computing? If you will talk about the computing, there was an aim to speed up, get the speed up, improve the performance of the machine. And what was the initial process to do that? Improve the processor capability, improve the processor capability. And why we were doing that? We were increasing the number of transistors which are available inside our processor. On the basis of that, there was a scientist, Gordon Murray, who has made an observation that in every 2 years, the number of transistors count get doubled inside the chip, the processor chip, and accordingly, its processing capabilities were increasing. And that concept were true for nearly 30 years. 30 years that concept has followed. Like if you see this graph says from the initial 4004 processor to Pentium 4 processor, that concept has followed. In every 2 year, the total count of transistor inside a single chip, processor chip, has been doubled, and accordingly their processing speed has been increased. But after that, what happened? Due to some physical constraint, now it's not possible to put more number of transistor inside a single chip. Okay, it's not possible to improve. There was a problem, physical constraint problem called power density. I'm not going into in detail of that, but due to some physical constraint, now it's not possible. So we have started searching for other solution. So what we have done, we have gone for putting the multiple chips inside a single CPU. Okay, or now we are having the multi-core CPU, and sometime we work on the concept of multi-threading. Okay, so these were the concepts which were derived to improve the performance when we were not able to increase the number of transistor count inside one single chip. So we were started working on that, and all of them internally working on some kind of parallelism. Okay, like when we talk about multi-chip parallelism, so what we have done, we have several physical processor chip inside a single computer, and what they are doing, they are sharing the internal resources. Basically, most important thing is the memory. So they were sharing the memory, and all mm, the processor chip were present inside a single computer. Okay, so the first way to improve the performance was multi-chip parallelism. And after that, the concept comes the multi-core parallelism. In case of multi-core is very much similar to the multi-chip. But what is happening in case of multi-core, we were having a single chip, and that chip is having multiple core processing core on that. Like today's CPU which we are having, those are 4 core or 8 core CPUs. Okay, 8 core processors. So they are having multiple cores are present inside a single chip. So what was the advantage of that? Like when it come to in compared to the multi-chip, the multi-core were able to share the resources even which were present on the chip, like cache memories. Okay, so the communication between those processors get faster. Then the third concept is multi-context or multi-threading. Multi-threading, with the help of multi-threading, we were achieving the parallelism to find the speed up. Okay, so multiple threads, multiple contexts were created, and what we are doing, multiple contexts were created, and all these threads are sharing the single processor. single processor on the basis of context switching. So our program we are getting more our program we are getting, which is having 2 3 threads running parallelly, it was getting more times, it was getting the CPU for more times, okay, and improving the performance. So these were the concepts which were used to improve the performance of our CPU. Now, because we were not able to increase the processor count, so we have gone through the different ways, okay. But what is happening, like in these days, we have the multi-core CPUs, but CPUs are most of the transistors which are available on the CPUs, they are used for the logic operation and the cache operation. Okay, all of them are not used for the computing purpose. So the a new concept come. What we do in with this multi-core processor, add a accelerator core with a multi-core processor in our machine. Why not we go ahead and add a accelerator core in our machine? Okay, so from there this GPU computing concept come on a picture. So these days the accelerator which we are using is a graphics processing unit, our GPU. Okay, so what is this GPU is, and why this GPU come in a picture? This GPU come on a picture because of gaming industry. Okay, so these graphics processors are actually initially created for the graphics operation, and uh, we were using these graphics processor for the video games which are having very rich visual over there. Okay, so for generating from one to generate one scene to another, we are required large amount of processing. Okay, we are required large amount of processing, and that processing were done with the help of graphics card. This Nvidia corporation has created the first graphics card, GeForce 256. Okay, but the purpose of that graphics card for just for the game, they have created it for the gaming purpose. Okay, so those GPUs. So what is GPUs? A graphics processing unit is a single chip processor that is used for computer display purpose. Okay, computer display purpose. But internally, what is happening over there? GPUs contain multiple small processing core on single chip. Okay, and these processing core can run parallel. They are having very small processing core. These cores are not equivalent to the core of our CPU. They have small capability, small capabilities. Okay, but they are efficient to do the arithmetic logic operations. So what happened over there? The GPUs are going to have a large amount of small processing core, and the beauty is over here is this: these cores can run parallel. Okay, so what is happening in case of graphics processing? What we are doing in case of we were having, like in a video game, from one scene when we need to generate another scene, we need to process all the pixel in one go, all the pixel of that scene in one go. So different pixels, what will be the new value for that pixel in a next frame image, that was processed with the help of different cores of GPUs. And that's way the processing got very fast for generating the next scene. Okay, and what is happening, the GPUs work on concept of multi-threading. Multi-threading, we'll talk about it in detail how that is happening. So they're working on a multi-threading. We write down a function, and that function is going to get executed by different logical threads, and these thread will execute on different processing unit. Okay, so in this way they are going to all of them are going to execute parallelly. And like I have already told you, the first GPU were created by the Nvidia corporation, is GeForce 256, and GPUs can do billions of calculation per second. Like Titan 5 can do 100 plus teraflop operation per second, floating point operation per second. Okay, so they are very good in processing. The GPUs are really good in doing the computing. Okay, this is the comparative image of CPU and GPU. Like the today's CPU can have 4 core, 8 cores. Processors are available these days. When we go to the GPUs, GPUs are like this. They have internally some multi-core, and each multi-core is having multiple processing unit. These small white boxes, square boxes, are actually showing the processing core over here. Okay, so one GPU can have one GPU can, like this Titan 5 is having nearly 5,120. Yes, do I remember? 5,000 plus processing cores are there. Okay, 5,000 plus processing cores are there. So just imagine that you can run 5,000 parallel thread in one go. So by theoretically it can um, improve your computation by 5,012 times, but 5,120 times. But that's not the actual speed up which we are going to achieve. We will talk about that and how the actual um, parallelism achieved inside the GPU, because we have to manage so many things. That's going to take um, some time as well. Okay, so that's about the graphics card which is available today. So what we were doing initially, we were using these graphics card for just the graphics purpose, and uh, people were using it in a gaming purpose. Okay, but in somewhere 2003, 2004, what people started doing, they start thinking how we can use these multiple processors which are available inside this GPU, how we can use it for the general purpose computing. General purpose computing, it means other than the graphics operation. How we can use it for the sorting operation, searching operation, or how we can use it for the graph processing and normal image processing, how we can use it. So from there, the concept of GPU computing come on a picture. Okay, and sometimes call it GPU, general purpose computing on graphics processing unit. That's the GPU computing. Okay, so what we are doing initially, we were trying, when these CUDA or OpenCL concepts were not available at that time. What we were doing, people were trying to map their problem in the graphics problem. Whatever problem they are having, they are map it to some kind of graphics problem and then assign it to the GPU for the computation. But that's the tricky job. That's the tricky job, because at that time there was no GPU compute engines were available. Like today's we have the CUDA and OpenCL's GPU compute engines libraries are available with us, with the help of which we can easily write the parallel code, okay, and assign those parallel code to the GPU. Okay, so what is happening? This GPU, what the GPU is doing, it is it is the utilization of GPU to perform the computation for scientific and engineering applications. GPU uses the GPU as a co-processor of the CPU. Okay, as I have already told you that this GPU cannot replace the CPU. It's always going to work as a accelerator with the CPU. Okay, so what is happening over here? What we do, compute intensive, or we have to do some kind of repeated work. That repeated work will be offloaded to the GPU or assigned to the GPU to execute it. Okay, so whatever program we wrote here na, that program will be in a heterogeneous in a nature. So what is the meaning of heterogeneous in a nature? It means that program will have the serial part, and that program will have the parallel part as well. So serial part is going to get executed on a CPU side, and parallel part will get executed on the GPU. And sometime, like today's GPU, or if we take the example of CUDA architecture, which were created by the NVIDIA. This CUDA architecture providing us the facility to write a code which can execute at the same time. The part of code is going to get executed on the CPU side, and the part of code will be executed on a GPU side. We can overlap the operation of CPU and GPU. Initially, what were happening, that was like a serial code. Um, all the serial part will be available on the CPU side. They are going to get executed on the CPU side. Whatever parallel part we want to execute on a GPU, just offload that GPU, that code to the GPU. GPU will execute it, process it, and we will copy back the data to the CPU side. We will collect the data on the CPU side. That was the process. But now we have the facility to overlap the operation between the CPU and GPU as well. Okay, we are doing some kind of computation on the CPU side. At the same time, offload some data to the some computation work to the GPU as well. So that's also going to speed up our problem, speed up the solution of our problem. Okay, so that's about the GPU or GPU computing. Okay, so there are three companies basically whose graphics card are very famous: NVIDIA's, AMD, and Intel. And these are the three major vendors which are creating the graphics card and which we can use um, for this GPU computing purpose. Okay, now, okay, so we know that the graphics card are available for general purpose computing, but why we are using, why GPU, like they say, why we are using the GPU computing concept? Why we just don't go for the normal parallel computer? Why we are using the so the reason behind that is the GPUs are flexible, precise, and cheap. Okay, so whatever modern GPUs are available, they are highly programmable. Okay, we have the high level programming languages. You can use the Fortran, you can use the C++, or even Python, MATLAB. All those programming languages can be used to write your code and run that code on the GPU side. So modern GPUs are highly programmable. Okay, and we have the high level programming language support for them. We don't need to go for learn a new language from the scratch. Like if we talk about the CUDA is kind of extension of C++. You can write all the code in a C++ format, but some new features, some new built-ins are available, which you have to use to perform the parallel computing operation. Okay, but all the C or C++, if you know about the C program, you can start directly writing a CUDA program. Just learn some features, learn some new built-ins which are required to write the parallel version of the code. Okay, modern GPUs support high precision and they can work on a 32-bit floating point operation. So they support 32-bit floating point operation as well. So whatever computation we are performing on the GPU, they are going to give us the high precision result. Okay, and one of the important factor over here is its cost is very less as compared to other parallel machine. Okay, so if you will go with the concept of cluster computing, uh, you will have so many computers, you have to purchase so many workstation with similar properties. Okay, and create a cluster for that gonna be very costly as compared to the our graphics card. You can get the best graphics card in few lakhs, just 3 to 3 lakhs. You will get a graphics card which is having 4,000 to 5,000 parallel cores inside it. Attach it to your workstation, attach to it to your desktop. But you just need to check your desktop is going to support or not, because they sometimes they have higher power consumption requirement over there, no? So you have to check that before going for that state purchasing a graphics card. You should know which graphics card my system is going to support, or what is the basic requirement of the system for that any particular graphics card. You should know about that. Only after that purchase a graphics card. Okay. So that's about the machine side. So machines are having so many features, so many features. That's why we want to work with the GPU computing. Go and work with the concept of GPU computing. Use the GPU computers as a parallel machine, an alternate parallel machine to the solution of our problem. Okay. Now it's okay. The GPUs are available. Graphics GPU computing is available. You can perform. You can write a code which can run on a GPU. But when to use the GPU or when to use the concept of GPU computing, it's not like that. You have a problem and straight way you can go and use the GPU computing concept, and you are thinking that you are going to get a speed up over there. Your problem will get speed up just because you are using the graphics card internally over there. Okay, so you have to keep some things in your mind, like your problem should be data parallel. If your problem is a data parallel, what is the data parallel problem? Data parallel problem, like you have a large amount of a data and you have a set of instructions which are going to get executed on that large amount of data one by one, like if you are executing it in a serial manner. Okay, so you have a function, you have a simple function, and that set functions should be called multiple times, and every time it is working on a different data item. Okay, different data. So for that purpose, your uh, GPU or GPU computing concept will be good. You have to use the GPU concept, there will be no problem. Okay. Similarly, they said having high arithmetic intensity. Your problem should have high arithmetic intensity. The meaning of high arithmetic intensity is, like, arithmetic intensity is the ratio of arithmetic operation and memory operation in your problem. Okay, how much computation you want. If you want a large number of computation as compared to the memory operation, then it's good to go ahead with the GPU computing concept. Okay, so that's having high arithmetic intensity. The number of computation, number of calculation, different kind of calculation. Once you have got a data, perform a different kind of calculation on that data. If you are doing like that, in place of performing the memory operation, copy the data in a main memory and then read it back. If you are doing that, then it's not good. So if your problem is having high arithmetic intensity, then it's good to go ahead with the GPU computing. And third thing is having low flow control. So what is the flow control like? If you have problem which are having so many conditions inside it, if this condition is true, then go and do such and such operation, and the next time the second condition is true, go and do the different operation. If you are having such type of multiple if else conditions in your program, in your problem, the actual function which you want to execute on a GPU side, then it's gonna reduce your performance. Okay, because in GPU ultimately all the threads are going to execute same instruction at any time. Okay, if you are having multiple if and else condition, and that if condition is true for, like, you have created 1,000 threads, and that if condition is true for only 10 threads, so 10 threads now will execute parallelly whatever you have written inside the if condition, and all other 990 threads will be in a wait condition. So they are going to do nothing. And after that, when that if condition part will completed by those 10 threads, then the next instruction will be executed by all the threads at the same time. So ultimately what is happening, if your program is having higher flow control, then your your performance will be reduced. Okay, that's the job is not good for GPU computing. Okay. So before going to the GPU computing, just check that you have that your problem is like having these properties. It should be data parallel. It should be having high arithmetic intensity, and it should have the low flow control. Okay. So now we know that the GPU computing is available. GPUs are available, which can work as an accelerator with our CPU, where we can offload the compute intensive portion. But that compute intensive portion should have some properties like data parallel, having high arithmetic intensity and low control flow. If all those things are fine with you, okay, go ahead with uh, writing a parallel program which will execute on GPU. Okay, so now we are having a problem. We are having a problem, and we are thinking like, okay, we can write a parallel version of this code. We know about that. It's internally having the uh, parallel features. That problem is having the internal parallelism, data parallel or anything else. It is having some kind of parallelism inside it. So we are going for writing a parallel version of a code which will execute the GPU side. So for that purpose, some of the programming languages or programming environments are available today. Like one of them is a CUDA. I have told you one of them is OpenCL. That's the open source. Okay. So I have read it somewhere in some research paper. What they were saying, like if you are having the NVIDIA's graphics card and you are using the CUDA programming language, so CUDA is internally optimized to run inside the NVIDIA's graphics card. So you don't need to do much. You just need to write a parallel version of a CUDA code, CUDA kernel, okay, and rest of the thing will be supported by that CUDA environment. But if you are working with the OpenCL, you have to put most of the logic by yourself. How the system is going to work, how the scheduling will be done. Like you have created multiple threads. How like what happened? You have 500 cores available in your GPU, and you have created 1000 threads, suppose, to solve your problem. So how these 1000 threads will be scheduled to that 500 cores, that concept will be defined by you. Okay, you have to put all those concepts over there in case of OpenShield. So CUDA is easy to write, okay, and you can easily write a code which will give you the fast performance. But if you are a good programmer, if you want to, if you think you can do the better scheduling than the automated system is providing, you should go with the OpenCL as well. Okay, OpenCL को भी use कर सकते हो आप. It's up to you. But here we are going to talk about the CUDA programming environment. Okay, so what is this? This is called the Compute Unified Device Architecture. Okay, so it is general purpose parallel computing architecture introduced by NVIDIA. Okay, NVIDIA has introduced when the GPU computing concept come on a picture. Like initially, people were using it for the gaming purpose, but after some time, people started using GPUs for general purpose computing. Then this concept come on a picture, like um, how we can use GPUs for general purpose in an efficient way. For that purpose, this compute unified device architecture come on a picture, and NVIDIA has introduced that. Okay, so CUDA gives a power to parallel compute engines in NVIDIA's GPU to solve the complex computational problem. Okay, so they have proposed a parallel compute engine over there that is going to support fast processing. Okay, CUDA comes with the software environment that allows developers to use C++ as a high programming language. Now, Fortran, even though Python, you can use all those things. You can use with the CUDA programming. Okay, so it is having the high level language support. And this CUDA architecture is having some features, the key features like thread hierarchy, multiple level of memories, and barrier synchronization. Okay, so if you are using the CUDA programming environment, so in CUDA programming environment, like I said, it could be possible that you have a problem, and for that problem, you want to create 1,000 threads. So they have the facility of thread hierarchy. What is this? That thread hierarchy facility, well, you can arrange those threads. So threads are arranged inside, like there will be a group of thread. You will create a group of thread that is called a block. Then you will create a block of threads, group of block that is called a grid. Okay, so ultimately a grid of threads will be created, and this grid of thread will be given to the GPU for execution. Okay, so the CUDA is having multiple thread hierarchy, multi-level of thread over there. After that, they have multi levels of memory. So memory is available inside your graphics card. uh, they have the procedure to use that RAM available over there, external memory available in the GPU, and then the memory available internal to the core. Okay, so they have the concept how to use that multi-level of memory, and then they have the concept of synchronization. Sometime uh, when the threads are running, threads are some different threads are doing different kind of operations. So you could write a barrier inside a thread, like it should wait for thread number xyz. Okay, and you can synchronize the execution of those two threads. After this point, after instruction number 10, these two threads should executed together, something like that. So you can put such type of synchronization inside your program. Okay, just wait. So these are the facilities provided by the CUDA programming environment. Okay, so whenever we come to this, like CUDA programming architecture is available to you. So how this CUDA programming architecture understand how it looks, the graphics card, the graphics card which is available to you, how it sees the graphics card. Okay, so what is happening, like in your graphics card, it could be possible that, just don't look at this picture, just listen to me. It could be possible that your graphics card is having, like I told you, that graphics card is having 5,000 cores. If a graphics card is having the 5,000 cores, then this all the 5,000 cores are not available on the top of a single chip. What is happening? Those those cores are grouped together, and one streaming multiprocessor is defined. Okay, so inside graphics card, you will have multiple streaming processor. Okay, and inside those streaming processor, you will have the actual processing cores. Okay, like as we see in this uh, image, our graphics card is having multiple multiprocessor 1, multiprocessor, like multiprocessor 1, multiprocessor 2, multiprocessor M. So a graphics card have multiple streaming multiprocessor. It is called the streaming multiprocessor. Sometimes we called it SMs. SMs, S and M, just SMs. Okay, so a graphics card can have multiple streaming multiprocessor inside it. Then every streaming multiprocessor will have multiple processing unit inside it. Like in our image, it is having, like in this figure, processing P1, P2 up to Pn, I think. So it is having multiple processing unit. These are the actual processing unit which is going to perform the execute the threads. Okay, then every processor, every multiprocessor is having a shared memory. The shared memory, this memory is shared between all the processing unit which is present inside one SM. Like this multiprocessor is having n number of processing unit or n number of cores, then all these cores can access this shared memory. Then every core is having its own register memory as well. Okay. Then every multiprocessor is having a instruction unit. Okay. So what is happening? What will happen during the execution? At any given cycle, each processor in the multiprocessor, each core in the multiprocessor execute the same instruction on a different data. That's the concept over here. Okay. And that instruction will be issued from our instruction unit. So one instruction will be issued, like you have a program, that program is having multiple instruction. So one instruction will be issued by this instruction unit, and all these processor will execute the same instruction, but they are going to work on a different data. Okay, and we will know how they will identify on which data we have to work, which processor, like suppose thread number one is running on a processor number one, thread number two is running on a processor number two. So how that thread will identify it, oh, okay, on which particular data I have to work. Then the next thread, how the next thread will identify on which particular data I have to work. Okay, so we'll talk about all those things. Then there is a device memory. Device memory, like device memory, actually the initially when we define whatever data which we want to process with the help of these GPU cores, that data should be available on the device memory. Okay, so when we will see a program in the most in the next session, hands-on session, I will show you before start of the execution of any thread, we have to copy our data from CPU memory to GPU memory. Data is available on the CPU memory. We have to copy the data from the CPU memory to GPU memory. So whatever data which is available on the GPU side, these processor will access it and process it. Okay. So there is a device memory where we have to copy the data. There is a concept of this constant memory and texture memory as well. Initially, these memories are available on this device memory, these data, but during the execution, these memory which we have defined as a constant memory or texture data, that will be copied to the cache of multiprocessor. Okay, so that's why they call the constant memory and texture memory get cached on the chip, that get cached on the multiprocessor. So you know the constant memory, what is the constant, you define it constant data. That's very much similar to that. And the texture is actually used for the graphics operation. Most of the time it is used for the graphics operation. So whatever memory we define inside the texture data, it's used for the graphics operation mostly. Okay, so this is the way how a CUDA architecture sees the GPU available over there. Okay, GPU for the CUDA architecture, GPU will look like something this. Okay, so it's the same thing I have written over here. I think at the hardware level, each GPU device is a collection of streaming multiprocessor. Okay, each multiprocessor contains 32 processing cores. 32 processing cores. Okay, and each processor has its local register memory. You know about the concept of the register memories. So whatever data currently executing by the processor, that most of the time it available in the register of that processor. Okay, so each multiprocessor contain 32 processing cores, and each processor has its own. So each processor, it means its processing core, we are talking about the processing core. Each processing core has its own local register memory. Each multiprocessor has its own shared memory, which is accessible to all the processor inside it. Okay, so what we do sometime, if we know this set of thread is going to work on data item 1 to 10. 1 to 10. So what we do, like we have created 100 of threads. Out of those 100 threads, first 50 threads are going to work on a data item 1 to 10. Every time they have to work on a data item 1 to 10. So what we do, in place of copying these data item to global memory of the GPU, it's good idea to copy it from global memory of GPU to the shared memory of a streaming multiprocessor, where those threads which are accessing that data are running. Okay, because the sharing accessing the shared memory will be faster as compared to the global memory. Okay, so processor whenever going to access the global memory, it will be, it's going it will take more number of cycles as compared to the accessing the shared memory. Okay, so that's why it's good idea to copy the data which is accessed continuously by a set of threads into the shared memory. Okay, all processing core in a SM can access. So all the processing core which are present in a streaming multiprocessor, they can access the global memory. So it's kind of global memory can be accessed by any processor, any core which is present inside any streaming multiprocessor. कहीं भी कोई भी core present है, that can that core can access the global memory. Okay, and I have told you each SM is having its local instruction unit. So what is happening? Your GPU is having multiple SM, and every SM is having its own instruction unit. Okay, and that instruction issued by instruction unit present in a SM will be executed by all the processor which are all the core which are present inside that SM. So that's the concept of CUDA hardware model. Okay, that's the way the CUDA understand about how actually internally that GPU device look like. If you have written a program, so how internally it will be look like by a GPU. Okay, that's about the CUDA hardware model. I hope you have understand it. Okay, now, like a very simple example, I will come to the programming model, but before that, uh, like we have vector addition problem. Suppose we have a vector addition problem, and you know, in case of vector addition, we have here two vectors a and b, and if you want to perform the addition of these vectors element wise na. So vector a is having 1000 element, b is having 1000 element, and what we are doing, we are making a of I plus b of I is equal to c of I storing the whatever value we are getting after performing the addition, element wise addition on these vectors. Okay, so if you if you are working on a GPU computing, your data should be big enough to at least see the performance improvement. If you are having the data of size just few thousands or few lakhs, you will not see any difference in a serial and parallel computation. Okay, sometimes it could be possible that your serial code is executing faster than your parallel CUDA code, because your data size is very small. Okay, and today's CPUs are very efficient. And if you are doing the parallel computation using the CUDA, for that purpose you have to copy the data from the CPU to GPU. You have to generate multiple threads, distribute those threads between different processors. So there will be an overhead. So your problem should have enough amount of data. Okay, so that you should be able to see the performance gain over there, performance improvement as compared to it should be in terms of some millions of or billions of data amounts data should be there. Okay, then only you will see the performance. So if you are having the vector addition problem, so what we do, if you will go to the CPU implementation of this vector addition problem, what we do simply, there is a function. That function That function, what that function is doing, you have passed uh, the vector a, vector v, and vector c to that function, and how many elements are available on that function. Like simple, just you have just put a simple for loop, a simple for loop, and for loop is going to run for 0 to the number of element over there, and it uh, performing the addition of one element at a time, okay, in a serially. So if 1,000 elements are available, so this for loop is going to run 1,000 times. So that's the serial implementation of that vector addition. Very simple example of vector addition. But what's going to happen if you want to perform this? You want to perform this 1,000 operations should be performed. 1,000 loop execution should be done in one go, in one iteration. Like if one iteration, all those 1,000 operations would be performed. So here you can use it for, you can use the concept of GPU computing. You can assign this job. Here it's element count is 1,000, so it's not large, but for just for the understanding, what you can do, you can assign this repeated operation, this looping operation to the GPU. Okay, and what you can do, you can create 1,000 threads. 1,000 threads will run parallel, and one thread will be going to perform one addition operation. So just think like theoretically you can think. So whatever time this operation will take for the one iteration of a for loop, in that time all the operation will be done, just like that. So what is happening over there, very much similar to that function. I'm just telling you this. GPU CUDA programming is very simple. No, कोई बहुत ज़्यादा, there is no extra brain you need to put. It's the function. This is the CUDA function, the same function. Just the way of writing will be different. Like you have to write it underscore underscore global underscore underscore. That's the way. Then the void. You are not going to return anything from this function. Then the function name, and very much similar to you have some pointers over there which are going to catch the vector. So there's a pointer a, pointer b in device, a in device, b in device, and c in device. Okay, you got this, you have passed this. Now inside this function is going to get executed inside one CUDA thread. So what will happen now, just listen to me. Like what we need to do, we have to create 1,000 threads, because our vector is having 1,000 elements, and we want one thread should perform the addition of one vector element. Okay, one element of a, one element of b, add it and store into the c. But important thing is here that you have created 1,000 threads, but you have to tell which thread is going to work on which data item, and how that will be evaluated. That will be evaluated inside the thread. That will be evaluated inside the thread. For that purpose, like I have already told you guys, I will talk about that in detail as well when we'll talk about the CUDA programming model. So what is happening, you are going to create a multiple threads. Group of thread will arrange, that will be called a block, and then the block will be grouped together, and that will be called a grid. So inside a block, every thread will have a unique ID, and that will be accessible by this thread ID x dot x. Inside every block, a thread will have a unique ID. So that will be accessed by thread ID x dot x. Then inside a grid, every block will have a unique ID, and that value will be accessed by block ID x dot x. And then here block dimension. How many blocks are, how many threads are available inside a block. That is the block dimension. With the help of these three values, okay, when the CUDA threads will be created, for each thread, these values will be unique. And with the help of these values, we will calculate the value of ID. We have calculated a variable. Now this is the position. This ID is telling the position to a particular thread which is executing this function on which particular data item you have to work. Okay, so this function is called the CUDA kernel function. Very much similar, like it's very much similar to the simple implementation. If you have implemented a vector addition operation with the help of a function, very much similar to that, we have written a CUDA kernel function. CUDA kernel function for the vector addition. And what this kernel function is going to do, kernel function will execute inside a thread, and with the help of that thread unique information, like what is the thread ID, what is the block ID in which that thread belongs, what is how many threads are present inside a block. With the help of this information, we will create a unique number. That number will tell, okay, on which data item addition operation I am going to do. Okay, so the CUDA kernel is a user-defined function. When it is called, it executes n times in parallel by n different CUDA thread. Okay, in each thread, kernel evaluates a index value. This index value I index value and thread works on data stored on that index. That's the concept. Okay, so we have written a kernel function. That kernel function is going to get executed inside a thread. Inside, when that kernel function is executing in a particular thread, this unique index value will be calculated, and this unique index value will be used on which particular data item that thread has to work. Like here, we have the simple addition operation. You can have the multiple operation over here, like a underscore d id is multiplied by 4, and then under root, and then some other operation, and finally you have to do the addition after 5-10 different calculation, and now you have to do the addition. Okay, so the important thing is that how this id value will be calculated. Okay, if you know that which thread is going to work on a which particular data item, 90% of the CUDA programming is done. If you have during the CUDA programming, if you have analyzed that, okay, I am going to create the 1,000 threads, and which thread is going to work on a which particular data item, you have identified that. Okay, that's you have written a very good kernel function. Okay, now we know the CUDA hardware. CUDA understand hardware is available, GPU is available. GPU is having multiple streaming processor. Each streaming processor is having 32 core inside it, 32 core inside it. So there is a concept called CUDA programming model. CUDA, what the CUDA programming models are talking about, how to map the threads into the hardware. Okay, how we are going to map the threads we have created into the hardware, so that our threads should execute efficiently. No CUDA core should be free at any time. That should be the way of efficiently modeling the number of threads. Okay, so there is a concept of arranging the threads. That's called the CUDA programming model. So what it is, so CUDA programming model tells a collection of thread running in parallel. CUDA programming model is about the how the collection of thread are going to run parallel in GPU. A collection of thread is called a block. Like we have to create 1,000 threads. So we are not going to write anywhere, okay, create 1,000 threads. What we will do, we will create a block. We will create a block. Suppose what we have done, we have created a block of 100 threads. So a block will have 100 threads. So actually we need 1,000 threads. So how many, we have to create 10 of this type of block. So what will be the block size? One block will have the 100 threads. Then number of blocks, 10 blocks. So that's the thing over there. The collection of thread is called a block. A block can be one, two, or three dimensional. Just keep it in mind. One, two, or three multi-dimensional block you can assign. But till now, whatever example I am taking, we are just talking about one-dimensional block. One-dimensional block. You have created a block which is having 100 threads inside it. Now, when a block is created and that thread block is having 100 thread inside it, every thread inside that block will have a unique id which we have seen in the kernel function now. That unique id will be accessible by thread id dot x, and this unique id for thread inside a block will start from 0. First thread will be indexed 0, second thread will be indexed 1, next thread will be indexed 2, and suppose we have created 100 threads inside a block, so 0 to 99. 0 to 99. So you have 100 thread inside a block. Every thread will have a unique ID 0 to 99. Now, the next thing is called a collection of block is a collection of a collection of block in a single execution is called grid. Now, this block is not the complete thing. You have to create multiple block. Like in our example, if we want to create 1,000 threads, one block is having 100 threads. It means we have to create such type of 10 blocks. We have to create 10 block, and every block will have 100 threads. Very much similar to that, like every thread inside a block is having a unique ID. Every block inside a grid, this collection of block is called a grid. Every block inside a grid will have a unique ID, unique block ID. That block ID will be accessed by block ID X, where built-in variable which is available in a Buddha programming. Okay, so block id dot x, and what will be the id? This id will start from 0. First block will have the id 0, second will have the 1, the 2, and then the final one in our example will have the 9. Okay, so in this way we are going to arrange 1,000 threads inside a grid. We have created a grid of blocks, and every blocks is having 100 thread. Our grid is having 10 block, and our every block is having 100 threads. Okay, so that concept is called CUDA programming model. CUDA programming model. Okay, so whatever example I'm talking about, it's one-dimensional arrangement of threads inside a block, one-dimensional arrangement of a block inside a grid. But what happens? Sometimes it could be the requirement you need to create millions or billions of threads. Okay, you can create the millions of threads, and sometimes if your data is multi-dimensional, very much similar to that, you need to create multi-dimensional block and multi-dimensional grid. For that purpose, you can create a block which is having multi-dimensional thread arrangement inside it. Okay, suppose you have created a block where the thread are arranged in a two-dimensional way. All these things are logical concept now, logical concept of thread arrangement. So suppose you have created a block. Inside that block, threads are two-dimensional, having two-dimensional arrangement. Then every thread will have two IDs, two unique IDs inside the block, like very much similar to the uh, inside a matrix. Every value will be have two reference now, x, one reference for the x direction, one reference for the y direction, very much similar to that. Every thread inside a block which is having two-dimensional arrangement of a thread inside it will have two id, one id for the x direction and another id for the y direction. And why we use the multi-dimensional block? To increase the number of uh, number of threads, because in one side one inside one block you can have maximum 1024 threads in a single direction. If you are having one dimensional arrangement of a thread inside a block, you can have maximum 1024 threads, not more than that. So if you want to create more number of threads, so you can go for the multi-dimensional block which is having the multi-dimensional arrangement of a thread inside it. Very much similar to that, you can have a grid which is having multi-dimensional arrangement of blocks inside it. In that case, every block is going to have multiple unique id, one id for every direction. Okay, so that's why I was telling, like in GPU in CUDA programming, if you have logically defined which data item is going to be accessed by which particular thread, by using your logical thread arrangement, your CUDA programming, 90% of your CUDA programming has been done. Okay? That's the actual concept which we need to follow to do the parallel computing over here. Okay, so that's the CUDA programming model. Okay, that's the same thing I have explained over here, explained with the diagram over here, CUDA programming model example. Like here, I have created 10 blocks. This is the grid. This is the grid. Logical arrangement of a thread inside a grid. And one side, we have one dimensional arrangement of a block inside the grid. Okay. First block is having block ID x dot x is equal to 0. Second block is having block id x dot x is equal to 1. Third block is having block id x dot x is equal to 2. And the final one is having the id 9. So what is this? These are the blocks. These are the independent blocks of a different colors boxes over here. Okay, this green, last green one is one block. This blue, this sky blue is different block. This orange is showing different blocks. Okay, and then inside the block we are having 100 threads. For our example, 100 threads, and each thread is going to have unique id. So this is the thread number 0, this is the thread number 1, thread number 2, thread number 3, up to thread number 99. So it's about block number 0. Now come to the block number 1. Again, in block number 1, thread will have the thread id 0 to 99. Very much similar to that, block number 2, all the threads will have number 0 to 99. Then finally, in block number 9, thread will have their id from 0 to 99. So this is the logical thread arrangement inside a grid. Inside a grid. Okay, inside a grid of threads, you can say. Like if we want to perform, if you want to, like whatever this orange color block is over here, if you want to know on which particular data item this thread is going to work, this thread is going to work, for that purpose we have calculated the id. So what is this? Block id x dot block dimension plus thread id dot x. For this block, thread id dot x is 2. Then block dimension inside one block, how many threads are there? 100, plus thread id x dot x 3. So it is going to work on 203 data item of our vector. Okay, so what will do? It will do a of 203 plus b of 203 is equal to c of 203. So it's a simple example where the thread will work on a particular data item. So if we are able to write a kernel function which is evaluating on which data item I have to work, and we have done the logical thread arrangement, efficient logical thread arrangement, then you will be able to write a good CUDA program, a very efficient CUDA program. Okay, so that's all about actually the basics of CUDA programming. CUDA programming, how the internal architecture of GPUs understand by the CUDA, and how the logical threads are arranged by the CUDA. This is all about that. Okay, here I have some points like where we are using the concept of GPU computing. GPU computing, like uh, applications area, neural network. Neural network are the today's neural network. Like when neural network, you know about in neural network, different neurons are going to perform some kind of operation, some very much similar operation, do the some addition of all the incoming bits and apply some kind of function. So we are using this GPU computing concept for the neural network training. Even though for the deep learning concept, the new concept come in a picture, like we are using the tensor core. Today's graphics card are also having the tensor core, okay, inside it. Other than these CUDA core, the graphics card are also having the tensor core. And tensor core are application specific hardware. They are not going to do anything else. What they do, they are optimized for doing the multiplication of matrix of 4 cross 4, something like that. So they are in one cycle, they are performing the matrix multiplication of 4 cross 4 matrix. Okay, they are internally designed hardware. So what is happening, today's GPUs are having so many tensor core inside it, which are efficient to perform the matrix multiplication. And in case of neural network, how many different multiple times you have to perform the matrix multiplication operation. Okay, they are efficient. These GPU computings are used for the graph processing. Okay, in case of graph processing, shortest path algorithms, k shortest path algorithms, and all those things, graph coloring algorithm, we are using the GPU computing concept to perform the parallel execution on repeated operation over there. Shorting algorithm, you already know, so many shorting algorithms are there. Merge sort, which are having the internal parallel features. And these sorting algorithms are multiple times used in a database access. So for that purpose, this GPU computing concept for implementation of parallel sorting algorithm is very efficient. Digital image processing, okay, these graphics cards were created for the graphics operation. So they are efficient for image processing, because in image processing you have to most of the time what we do, we have to perform different types of operation on similar operation on a different pixel of the image. So what you can do, you can assign one set of a pixel to one processor, one set of a pixel to perform that operation to one processor, and that operation will be done parallelly. Okay, weather forecasting, in case of weather forecasting, we have a large amount of data which we have to analyze. So wind direction and all those things also done with the help of GPU computing. Bioinformatics, in case of bioinformatics, we are using the concept of this GPU computing, molecular modeling, this particle dynamics, RNA, DNA, all things. We have so many research available where they are using the concept of GPU computing. Okay, then antivirus software. Internally, this antivirus software uh, to process the data which they access to find out the virus is available or not. They distribute the data to different core and process it. So all of the applications area which are using the concept of GPU computing, and there are many more as well. Okay, to give you uh, that picture how this important GPU computing concept is important. Like when we create a supercomputer these days, most of the supercomputers are internally using the graphics card, number of graphics card. So they are just not using the concept of GPU computing, they are using the concept of cluster, and they are using some kind of hybrid concept over there. Okay, multiple cores, multiple processing cores are available, and if every processing core is having associated GPU accelerator as well. Okay, like the best one the USA Titan, the supercomputer is having 10 petaflop processing speed, 10 petaflop instruction per second. It is having, you can see how many numbers of CPU, like 18,688 CPUs are there, and every CPU with CPU we have one associated Tesla K20 graphics card. One graphics card, Tesla K20 graphics card, is having 2668 core. So you can imagine how many cores are available, processing cores are available inside this supercomputer. And this supercomputer is having CUDA Fortron for parallel programming. This Titan supercomputer is using the CUDA Fortron parallel programming concept. This supercomputer Saga, which is available with the ISRO, having 450 teraflop top speed. It's having 700 Intel processor CPU core inside it, and 700 NVIDIA Tesla C2075 GPUs. And every C2075 Tesla C2075 GPU is having 448 cores. Okay, so you can imagine how many, you can calculate how many actual processing core this um, supercomputer is having. Okay, and this Shaga is using the CUDA C programming concept for the parallel programming. Okay, and finally for this session, let's see this video. This video, it's an old one, but it's talk about if you are using a CPU, how that CPU is going to work, and in place of if that work is assigned to a GPU, then how that GPU is going to. I'm playing this one.
All right, I introduce to you Leonardo, and he is going to paint a picture.
Abba, my screen is visible. This video is visible to you guys. Abha, you there?
For you guys, in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up.
So they have demonstrated this, the first one, if you are using the CPU to draw that image. So how the CPU is going to work. And in place of that, if you assign that work and somehow using the GPU, how the GPU is going to work.
Gentlemen, Leonardo 2.0. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes within which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In
10, 9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Hello, Abha, are you there?
Yes, sir.
Okay, so that's all about this session. Okay, and just wait a minute. Okay, so we have seen on this like why we have to go for the GPU computing, and what are the concepts available which help us to use the GPU computing concept, like the CUDA programming model is available. Some other models are also available. You can go with those models as well. But one of the best model which is available to us is the CUDA programming model, which is utilizing the NVIDIA's graphics card internally, and it is optimized for the NVIDIA graphics card. That's why we're talking about to use the CUDA programming concept. Okay, and I've already told you it's very efficient. It's easy to write. Very easy to write a CUDA code. You just need to understand how we have to assign a thread to a particular data item. That's all. Okay. So that's all about the basics of GPU computing. In the next session, I will try to talk about how this internal execution take place, how this threads we have created, how these threads will be assigned to the processors which are available in the GPU, and then uh, I will try to show you some parallel code, try to explain those parallel codes, and after that, finally run those parallel codes on a Google Colab. Okay, I don't have the machine with me at present, so I will try to run it in the Google Colab and try to show you how to use this Google Colab platform to run your CUDA code. Okay, so that's all, Abha.
Okay,
Okay.
sir. So thank you for the wonderful session, sir. It had very elaborated concepts, and you used examples and videos to explain all the participants, sir. Thank you, sir. And we hope our participants find these helpful in their research. Thank you so much, sir.
Okay. So I will join at next session. At what time the next session will start?
So at 2:30.
2:30 after 1 hour, near about, no? Okay, that's
Yes,
fine.
sir.
Thanks.
Okay, sir. Thank you, sir.
I have to join the same link.
Yes, sir.
Okay, so I will join it in somewhere in 2:30.
Okay, sir.
Thank you.